Here we have some data points, and our goal is to train a curve that fits these points so we can predict outputs for new unseen data. Now, a single straight line can fit this dataset, but it will be too simple to capture the pattern. This is called underfitting. On the other hand, if we try a very complex curve that fits the training data too well, the model ends up learning even the noise present in the data. As a result, it performs poorly on unseen data and does not generalize well. What we really want is a curve that's trained well, one that captures the true pattern in the data without learning the noise. Here is what typically happens during training. At first, both the training loss and the validation loss, that is the loss on unseen data, starts decreasing. But after a certain point, while the training loss keeps going down, the validation loss starts increasing. That's the moment when the model begins to overfit. This is what we call overfitting. If you are not familiar with terms like training error, validation error, or overfitting, I have already made a detailed video on that topic. You can find the link in the description box below. Now, when a model is overfitting, we say it has high variance. So, our goal is to find a way to reduce that variance. In other words, to fix the problem of overfitting. And this is where regularization comes into the picture. Regularization is anything we do to prevent overfitting and help the model generalize better. Now, when we train a model for too long or make it too complex, it often ends up with large weight values. That's because the model is trying too hard to fit every single data point, even the noisy ones. So it adjusts its parameters drastically to minimize the training loss. In contrast, simpler models usually have smaller weights since they focus only on the main trends in the data rather than the tiny fluctuations. So our goal is to train a model in such a way that the weights don't grow too large. Keeping the weights small helps prevent the model from reacting too strongly to the noise, and that's exactly what regularization helps us achieve. Now, let's take mean squared error as the base cost function. To control the size of our weights, we will modify this loss function slightly. We create a new loss function by adding an extra term called the penalty term. This penalty term is controlled by a hyperparameter called lambda, also known as the regularization hyperparameter. When lambda is bigger, the penalty is bigger. When lambda is smaller, the penalty is smaller. It's a fixed value that decides how strongly we want to penalize large weights. The penalty itself is the sum of squares of all the weights, which is known in mathematics as the L2 norm. So, when we add this L2 penalty term to our loss, this is called L2 regularization. During training, the optimizer tries to minimize the total loss, which now includes both the original loss and the penalty. Since large weights increase the penalty, the optimizer naturally prefers smaller weights. They help reduce the total loss without hurting the fit too much. This will be clear in a moment using geometry. But before that, let's see another type of regularization called the L1 regularization. Here we use the L1 norm, where we only take the norm of weights without squaring it. Now, when we optimize the new loss function, we take derivatives with respect to the weights. In the L1 case, the derivative of the penalty term depends on the sign of the weights, meaning it contributes a constant factor to the gradient, regardless of the weight's magnitude. In contrast, in the L2 case, the derivative is proportional to the weight itself. So, larger weights produce larger gradients and smaller weights produce smaller gradients. This term is then used during weight updates in gradient descent. It's this contribution that effectively shrinks the weights while training, helping the model avoid overfitting. Now, do not get confused by all the math and derivatives. Let's look at this geometrically, which could be easier to understand. Let's visualize this using just two weights, W1 and W2, because it's easier to see in two dimensions. For these two weights, the norms looks like this. The original mean squared cost function, without any penalty, forms elliptical contours. The point at the center, let's call it W1 star and W2 star. is where the original loss is minimized. Now, for L1 regularization, the constrained region forms a diamond. The size of the diamond is controlled by lambda. During optimization, the algorithm finds the point where the loss contour just touches the diamond. Because the diamond has corners, the probability of one of the ellipses touching the corners is very high, which makes some weights exactly 0. This is why L1 regularization produces sparse weights. In the L2 case, the constrained region is a circle. The optimal point is still where the contour touches the circle. But circles do not have sharp corners, so the chance of a weight being exactly 0 is extremely low. Instead, L2 tends to make all the weights smaller, but generally none of them exactly 0. This geometric view shows clearly why L1 encourages sparsity while L2 just shrinks weights. These regularization methods are not just for classical machine learning problems like regression, they are also widely used in neural networks. The concepts remain exactly the same. We add a penalty term to the loss function to control the weights, prevent overfitting, and improve generalization. Now, one thing you might be wondering is, why didn't I include a penalty term for the bias in the equation? The reason is simple. The bias term does not contribute to overfitting in the same way as the weights. The weights control the slope and flexibility of the model, which can grow too large and fit noise. The bias just shifts the entire function up or down. And for neural networks, bias is just a term inside the activation functions, and penalizing it usually does not help much. That's why in practice, we regularize only the weights and leave the bias unpenalized. Now, there is another regularization technique specific to neural networks called dropout regularization. I use this one a lot in practice. Here is how it works. Suppose we set p equals 0.4. This means each neuron has a 0.4 probability of being dropped during training. When a neuron is dropped, all of its connected weights and its bias is temporarily ignored in that iteration. Training proceeds only on the neurons that are not dropped, and both their weights and biases are updated. Before the next iteration, all neurons are restored, and the new set of neurons is randomly dropped according to the same probability p. This process, dropping neurons randomly and training on the rest, continues for every iteration until the loss is minimized. The intuition is that the model is prevented from relying too heavily on any single neuron, which helps avoid overfitting to noise. This encourages the network to learn robust features across all neurons, rather than depending on a few specific ones. Finally, when training is complete, all neurons are used for testing or deployment. This allows the network to make predictions with the full model, while benefiting from the robustness learned during dropout. Let's quickly look at the mathematics behind dropout. This is the equation of the weighted sum in layer L, along with the corresponding activations. If you are already familiar with neural network notation, you will recognize this. And if not, you can check out the deep learning playlist linked below. Now, we introduce another variable, RL, for this layer. It's a Bernoulli random variable, and here the Bernoulli random variable equals 1 with probability 1 minus p and equals 0 with probability p. This comes from the mathematics of probability. In simple terms, RL decides whether a neuron in layer L is kept or dropped during training. Now, we perform an element-wise multiplication between the R values in that layer and the corresponding activations. It looks something like this, where the matrix RL is a column vector of zeros and ones, sampled from our Bernoulli random variable. When we multiply them, any neuron whose R value is 0 will have its activation set to 0, meaning that neuron is dropped for this iteration. The remaining neurons keep their activations as usual and continue forward through the network. Now, there is a small problem with this approach. Remember that during training, we randomly drop a certain percentage of neurons. This means that the network sees fewer activation neurons during training than it will during testing. As a result, when we use the full network at test time, the total output becomes larger than expected because no neurons are dropped. In probability terms, this mismatch happens because of the expected value of the activations changing between training and testing. To fix this, we scale the activations during training by dividing them by 1 minus p, where p is the dropout probability. This ensures that the expected value of each neuron's output remains the same during both training and testing. In other words, the model behaves consistently whether neurons are being dropped or not. This specific version of dropout, where we scale the activations by 1 minus p during training, is known as inverted dropout. Now, in most real-world deep learning models, it's common to use a fixed dropout rate across all layers, but sometimes different layers can have different values of p. For the output layer, the dropout rate is always 0, meaning no neuron is ever dropped. Because removing output neurons wouldn't make sense, the network needs all of them to make predictions. For hidden layers, a dropout rate of around 0.3 to 0.5 is common. If a layer has many neurons, you might go for a 50-50 dropout, depending on the design. And in some cases, even the input layer can use dropout, usually with a smaller value like 0.1 to handle highly variable inputs. Sometimes, when we have very little data, the model can overfit because it does not see enough variety in the training example. One effective method to tackle this is called data augmentation, which is the next regularization technique we will talk about. Let's understand this using an image example. Suppose we have a single image of a cat and we want to create more training data from it. We can do this by applying simple transformations. For example, cropping the image, rotating it, changing colors or brightness, applying multiple transformations at once, like cropping and then adjusting color, blurring or adding small noise, and things like that. Each of these transformations generate new variations of the original image, effectively creating many training samples from just one original image. Data augmentation is not limited to images. It can also be applied to audio, video, or text by slightly changing their forms while preserving the information. One thing to keep in mind, although we generate many new samples, the information gained is not as rich as completely new data. So, there is a trade-off. It helps reduce overfitting, but it does not fully replace the value of having more real and diverse data. Another technique is called early stopping. In this method, we monitor the training loss and the validation loss. That is, the loss on dataset the model has not seen during training. Initially, both training loss and validation loss decreases, but after a certain point, the validation loss starts increasing while the training loss keeps going down. This indicates that the model is beginning to overfit the training data. With early stopping, we stop training at the point where the validation loss is smaller, preventing the model from overfitting and helping it generalize better to unseen data.